Today I'm going to be talking about error detection and correction. So you can sit and relax for the rest of the lecture. Just listen to me. All right. And you already, a lot of you should have covered this before. But if you haven't covered it, this is a good revision. The first part of it, today at least. So the first type of error detection used in computing, and the oldest, is called parity bit error detection system. Is the simplest, the oldest. And it works very simple. They're what's known as 8-bit, 9-bit error detection. It doesn't matter. We'll take one of them and we'll use it. And the same applies to all. So for example, if you're transmitting data, or if you're storing data, let's say this data here, imagine you're sending this data. It could be a long frame from one machine to the next, or you're storing it on a hard disk. It's also used for detecting errors in information that was stored. So the parity bit error detection system, the way it works, it takes this data, and when it sends it, it adds more data to it. It adds more bits. Imagine if this is the frame and this is the direction of transmission. So it will take 7 bits. This is the 8-bit parity error detection. It will take 7 bits of the user data. So it will take 1, 2, 3, 4, 5, 6, 7. So it'll take those 7 bits and it will insert in there an extra bit in bit number 8. It'll add 1 or a 0. And it will do the same with every, as long as you have data going, it will keep taking 7 bits and insert an extra bit. So 1, 2, 3, 4, 5, 6, 7, it will insert another bit, and we call this the parity bits. So the sender keeps sending parity bits, and the receiver would remove them, but after doing the error check. Now, does the sender add in a 0 or a 1? So it'll add 1 bit here. It's either a 0 or a 1. And this depends on the sender and the receiver. They might agree we want to go for odd parity, or they might decide we want even parity. So there are 2 types of parity, odd or even. What does odd or even mean? It means in the full byte, 8-bit that's received by the receiver, they should be an odd, if we agree on odd, an odd number of ones, odd number of bits that have the value 1. Or if we agree on even, that means a number of bits received by the receiver in every 8 bits, an even number of bits. So now the sender will count 1, 2, 3, 4, 5. That's an odd number. Let's say we're going to go for even. The sender and the receiver agree for even parity. What does that mean? It means every byte that the sender will send will contain an even number of bits that have the value 1. So the sender will find how many bits do we have. If it's even, it will insert a 0 to leave them as even. And if the number is odd, it will add 1 more bit to make the total number even. So now we agreed on even. So this guy looks at these 1, 2, 3, 4, 5. There are 5 ones. That's odd. We have agreed on even. Then I better insert another 1. So it will add 1 here. And then it will count the next one. 1, 2, 3, 4, 7 bits. Those 7 bits have a total of 1, 2, 3, 4. They have 4 ones. So this one had 5 ones. We better add a 1 to make them 6. This one has 1, 2, 3, 4. That's even number. Then we better not add any more ones. What we do, we add a 0. So the sender will always add a 1 or a 0 to any number of bits they agreed on. Let's say in this case, every 7 bits we take from the data, we must add a 1 or a 0. Now, when the receiver receives these, now the receiver receives, so this is the string that's transmitted, so the receiver received 1, 1, 0, 1, 1, 0, 1, 1, followed by 1, 2, 3, 4, followed by 4, 1, 2, 3, 4. So that's what the receiver receives. This is the frame received. It contains parity bits. They need to be removed. But before they're removed, we do a narrow check. If one of the, let's say this is normal, if everything goes correctly and nicely, nothing changed. This is exactly what the receiver will receive. We'll say, okay, let me take every 8 bits, 2, 4, 6, 8. So these are 8 bits. This 1 byte, there's another 8 bits. Every byte should contain an even number of ones. So it will count. 1, 2, 3, 4, 5, 6. There are 6 here, that's good. Let's count 1, 2, 3, 4. There are 4 bits that have the value 1 in this one, and everything is perfect. Now that's the first step. The second step that the receiver will do is say, okay, let's get rid of the parity bits. It knows where the parity bits are. It's the last bit in every byte, so it will remove this one, and then it will go and remove this 0. And now the information is exactly the same.
Why we are deciding 7 bits for this?
I think there are 7-bit parity systems, there are 8-bit parity systems. So it depends on whichever one we will use. Now I just decide, okay, let's go for the 8-bit parity system. It could have been 9. Some systems use 9. So whatever is in use, but the same rule applies. The sender always inserts 1 extra bit to every byte. The receiver will remove that bit later on from every byte, but the sender adds in the 1 bit or the bit at the end of every byte to ensure that the total number of bits that have the value 1 is an odd or an even, whatever we agree on. And the receiver will confirm that, and if everything is correct, then there is nothing changed. Because sometimes, let's say now, this sender sent this data, we agreed on even parity, the sender added an extra bit to make sure every byte contains an even number of bits, but when they were received, this is what we received. 1, 1, let's say 0, let's say this 0 by mistake during transmission. Some noise caused this one to change into a 0, 1, 0, 1, 1, and then the next byte is 1, 1, 1, 1, 0, 0, 0, 0. So now the receiver received this frame, and you're asked, okay, you are the receiver, the sender has sent you this frame using the even parity bits. It means you are a receiver, every 8 bits should contain an even number. So first 2, 4, 6, 8, so that's 1 byte, and that's 1 byte. Each one of those bytes should contain an even number of ones in them. So let's look at the first byte. 1, 2, 3, 4, 5. Oh, 5, that's an odd number. There's something wrong with this byte. If you count the next one, 1, 2, 3, 4, that's 4, that's good. But we don't even carry on testing anymore. If the receiver finds any byte that has the wrong number of bits that have the value 1, like if we had agreed on even, we find an odd. If we had agreed on odd, we find an even. That means there's something wrong and the full frame is discarded. Okay, so this is a simple parity bit error detection system. It's a cooperation between the sender and the receiver. The receiver adds in a bit to every byte, and the receiver will remove that bit. So we don't want to change, because if you send me a file, I don't want to receive a different file, that has more information in it. We want exactly. So whatever the sender sends, the receiver will remove. Whatever the sender sends is known as redundant data. Redundant data is like, this is a cost. To do something useful, sometimes it has a cost. You have to carry more information that are not part of the user information. So This is one way to evaluate which system is better. If you have two systems that do the same thing, but one carries 1,000,000 redundant bits and another one that carries 10 redundant bits, of course, take the one that carries the less redundant bits, because if that's extra cost. Remember, these bits need to be transmitted. If they charge you per bit, then you'll end up paying a lot of money to transfer your data. So if you're sending 1,000,000 bytes, then you might end up having to send with them 100,000 bytes. So 1,100,000. That will affect the total amount of data that you can transfer for users. So that's an extra weight. This is like an airplane that flies and say, okay, I can take passengers with the weight of 20-ton passengers. Yeah, great. But now the airplane has to carry another 20-ton weight of fuel, so it cannot take the 20. So that extra fuel is needed, but it's an extra weight that makes the airplane not efficient, because it has to carry the passengers and the fuel as well. So it's an extra work that needs to be done, in this case by the transmitters and receivers. Transmitters and receivers have a limited capacity, 1,000,000 bits per second. Now if you have to carry user data of 1,000,000 bits, oh no, you have to add another 200,000 maybe of extra bits. So that's called redundant data. So anytime, well, first you need to know what redundant data is. It's the extra information that needs to be carried or generated by the system or by the network, and they're not part of the user data. Normally added in by a sender and removed by the receiver, but they have to move along with the data, and that's the cost, the delay that they cause to the data. So anyway, so this is the parity bit error detection system. It's the simplest, the oldest system. How good is this system? Anybody can spot any problems with this system? Or issues, yeah? Yeah. All parity systems has this problem. Let's say the sender sent this information, and here we showed that we had an error. This one turned into a 0. But imagine if the other one turned into a 0 as well. Let's say this bit changed and also this bit changed. So now we have 2 errors. Will the receiver discover this error or not? So the receiver, all the receiver has to do is count how many ones are in this byte. So when the receiver counts 1, 2, 3, 4, he says, oh, that's good. There's no error. We have an even number of bits. When in fact we have 2 errors, not just 1. So that's a problem with parity bit error detection system. You have to add a bit to every byte. Some people say that's not a lot. That's okay. Maybe we can live with. That's not a heavy weight. In fact, it is. But for now, okay, let's say it's okay. And then the other problem, the major problem with parity bit error detection system, it does not discover all errors. It consists of 2 bits that flip, change, or forward, or 6 or 8. We will not discover them. It only discovers if the error involves an odd number of bits. Okay, so that's a major problem with error detection system. If it doesn't discover a lot of the errors for you, that's the job it should be doing. Okay, so that's called parity bit error detection system. In fact, with the redundant data, how much redundant data do you think this system will carry? Any idea? How much does it carry? How much redundant data we added to this? We added 1 bit to every byte, right? Yeah. Okay, so if we are sending 1,000 bytes, how many bytes do you think we'll be adding? Okay, if we are sending 8,000 bytes, we'll be adding 1,000 bytes, right? So it's a ratio of 1 to 8. 1 in 8. So every time you send 8 kilobytes, in fact, 1,000 of them, 1 kilobyte is not user information, it's redundant information. If you're sending 7 million bytes of user data, you have to append to it 1 million bytes. So it's a ratio of 1 in 8 or 1 to 7. That's a lot of weight by all standards. So we look at other error detection systems that they don't send that much. This is almost 10% of the transmission you make is redundant information. It's not really user data. So you're really automatically you're losing 10% of your transmission, wasting it on redundant information. So this error detection system has two major problems. It has a large amount of redundancy, and if you want to know exactly, it's 1 to 7, the ratio of redundant data to actual data, or 1 in 8, whichever one you say. And that's heavy. That's by all standards. It's a lot of cost, heavy cost. And the second problem with this system, it does not discover all errors. You need to know which errors it discovers and which errors it does not discover. So if there's only one bit in the frame change, that's okay, we'll definitely discover it. Now, the other thing is that if 4 bits change, or 3 bits, we're talking about in the same byte. Remember, this one we did not discover when 2 bits flipped in the same byte. But imagine if 1 bit here and 1 bit there, we discover them. But it will not discover, so listen to what I say. It will not discover 2 bits in the same byte. It will not discover 4 bits in the same byte. Okay, so, but if the frame is so big and there's 1 bit error here in 1 byte and 1 bit in another byte, we will discover the first bit with an error. Okay, so if you are asked what errors it does not discover, what would you say? Anybody give me a nice, concise, precise answer? What errors it cannot discover?
The error is even.
That answer would not get you full mark. He said if an even number of bits flip, what's missing to make it a bit more precise? I just said, if you have 2 bits, one in this byte and one in another byte, you still discover them. What's the condition? They have to be in the same byte, an even number, not just 2 or 4 or 6 or 8 in 1 byte. Okay, so they have to be in the same byte. Then it cannot be discovered. So that's one system. And this is the oldest system. It's been around since computers started. Anytime they used to send information to print it on the printer, things didn't go right, so they had to insert it. So it's almost a system that's ingrained, it's built into almost all computer systems. Storage, sending information from one device to a device to a printer, it's all built in. And it's a bad system, it's not a good system. It's very expensive and it doesn't discover all errors. But it's still the most used system today. Why? Because it's already built into the system and it probably costs more to take it out. So they said, just leave it. Because if they need to start taking it out, they have to remove it from every file stored in every hard disk in the world. Every file stored in your computer, every byte in that file has an extra bit. So when you read it, this happens in the background. The operating system will tell you, oh, sorry, there's a parity error bit in your file. That means, the file has 1 bit flipped. So maybe you don't trust this file. Okay, so every file stored on a hard disk or on a tape, every file sent to a printer to be printed, they use the parity bit error detection system. Why are they still using it? Because it costs too much to remove it. So just leave it. It's not perfect, we know that. So, okay, that's called the parity bit. So there was an attempt to improve it. And they used another system or an improvement of this system, and they called it the block parity system. So this is system number 2 we look at. You need to be able to explain this Or if you are given some data, and you say, if the question might say, hey, here's data received. It was sent to us by the sender using odd parity. Does it contain any errors? And you should be able to count every byte separately. And if you find a byte that does not have odd bits that have the value 1, then you say, no, there's an error there in this byte. We don't know which bit. The other bad thing about this, we don't know where the error is. We don't know which bit. We know it's in this byte. But is it the first bit or second bit? We don't know. Just one of them flipped. So that's another disadvantage. We don't know which bit. How do we fix this? You can't fix it because we don't know which bit. You have to send back to the sender and say, can you send me this file again? So the sender has to send the whole file or the whole frame, not always the file. So if you're a neighbor, you'll be sending information in a frame. You can say, oh, there's something wrong with this frame. Please resend it. And maybe a second time you hope it will be okay. But somebody came up with an idea and said, no, we can improve this. So let's say they called it the block parity. So the block parity system, it works on the same idea. Parity is still the base idea for most error detection systems. But okay, the block parity, they said, okay, let's take this data. If you have a long string of data, here it is. I'm going to put down, okay, so I'm going to take, so they say, okay, take 7 bits. But still, this is the block parity. We're going to add a parity bit at the end of every byte. But I'm going to put them now in a block, in a matrix, in a table. I'm going to take the first 7 bits, 2, 4, 6, 7, up to this point. So I'm going to write here 1, 1, 1, 1, 1, 1, 0. Now I'm going to add a parity in there. I'm going to take the other one, 2, 4, 5, 5 zeros, followed by 2 ones. So that's, and now I'm going to take 2, 4, 6, 7. So it's 1, 1, 0, 1, 0, 1, and a 0. So now here's the data. 7 bits, 7 bits, 7 bits. We're going to add a parity bit to every byte. This is like the ordinary parity bit. So now we're going to be using odd parity. So the sender is going to make sure every byte contains odd parity bits. So I'm going to start with you. What bit will the sender be adding here? If we were senders, yeah? Will I add a 1 or a 0? How do you know it's 1? Why did you say it's 1? Yeah, to make sure that the 1 byte now should contain an odd number. So first we count 1, 2, 3, 4, 5, 6. That's an even number. Let's add a 1 to make it 7. And that's how to make it an odd parity. Right, the second byte. Yeah? Will I add 1 or a 0 here? 1. Why 1? Because you count how many ones? 1, 2. That's even. Let's add another 1 to make it odd. That's how the sender will keep adding. In fact, as the sender is sending data, he's counting. And in computing, counting is not a quick operation. It does, it's just, XOR it, and whatever is left. That's like counting. It just puts a 1 or a 0. So there's a trick to it. So it's very, very fast. That's something else when you compare different systems. You need to worry about redundancy. Compare them. Which one has more redundant data? That's a bad one. Which one has speed or delay? The faster one is the better. This is very fast because it's just XORing. Remember, computers are very good at logical operations. That's ANDing, ORing, NORing, NANDing. These are the computers are the fastest. And addition, division, multiplication, they're really slow computers. So instead of dividing, they always do XORing or whatever it is. So in here, instead of counting, do I have 6 or 7 bits or odd number? It doesn't count actually. It actually XOR it, and whatever is left with at the end, it puts it 1 or 0 and goes through the rest of it. So, but it's very, very fast. but it has a lot of redundant data and it has a lot of errors not be detected. These are advantages in this one. Okay, to compare them, you say, right, how much errors does it detect? 100%, 90%, it's probably even below 50%. So this is really poor, the parity. But anytime you compare two error detection systems, check the redundancy, how much redundancy, how much of the errors that get discovered, and how fast it is. At least those three things. So now let's go to the odd one. So we made the information into a table, into a matrix. We still do the same information, the same work with every byte. Okay, up there. What bit will we add here? A 1 or a 0? A 1. Why? 1, 2, 3, 4. That's an even number, so we add 1 to make it odd. So that's exactly the same as the parity system. But now let's do the same for every column. Every column we do the same thing. So now and we add 1 bit at the end of every column. So we do it for rows and we do it for columns. Right? Who's going to help me there? I have a volunteer here, right? The guy with the white hat. Tell me, what value will you put down here? What parity bit? Did you say 4? 1 or 0? Are you sure? Okay. You count how many ones are in this column. 1, 2. They should be odd. 2 is an even number, so add a 1 instead of a 0 to make them odd. So now that's their 3. We're happy. What about the next one? Next 1. Okay, keep going. Same person. What bit will I write here? 0. Why? Because there's 1 here. That's an odd number. Okay. 1, 0, 1. 0 will make it even. Oh yeah. Okay. All right. We don't have to write the last one, but we can write a 0. Okay. So that's what we send now, and we send them 1 byte at a time. So we first send that. That's 1, 1, 1, 1, 0, 1, followed by 0, 0, 0, 0, 0, triple ones, and followed by 1, 1, 0, 1, 0, 1, 0, 1, followed by the last byte, which is 1, 1, 0, 1, 0, 1, 0, 0. So that's the frame now. You receive it as a receiver. What do you do with it? You get a long string. First you put it in a table like this. Imagine now that's what you receive. But even looking at this now, you can immediately tell that where are the parity bits? You count 1, 2, 3, 4, 5, 6, 7, 8. That's a parity bit. 1, 2, 4, 6, 7, 8. That's a parity bit. These bits we'll get rid of as a receiver. 2, 4, 6, 8. You get rid of the 8th bit. And what about this one? Do we get rid of the last bit? No, all the bytes. See, this last byte is not part of the user information. All this at the end is also needs to go. That's parity. Now, let's check. Are there any errors? Okay? I want you to look away now just for a second, and I'm going to flip a bit, and we see if we can discover it. Don't look. Hold on. I made the wrong one. Wrong color. Okay, I changed 1 bit. Now let's see if this system will discover it. All right. So there it is. You take those bits, you put them there in this table, and count. How many bits are there? 1, 2, 3, 4, 5, 6. Well, 2, 4, 6, 7. Sorry. 1, 2, 3, 4, 5, 6, 7. So there are 7 ones here in this row. And here there are 3 ones, right? Is everything okay? We guess. This one, 1, 2, 3, 4. Oh, 4. There's something wrong with this row. Now, let's go with the last one, 2, 4. No, leave the last one. You don't have to count the last one. Now, let's go with the first column. How many ones are there? 1, 2, 3, including the parity. That's good. Odd. 1, 2, 3. That's another good one. 1. That's another odd. That's good one. Odd. No, that's 1, 2. Oh, there's an even number. 1, 3, 1, and 3. Okay. So there's something wrong with this column, and there's something wrong with this row. So if the row and the column cross, it will tell you which bit that had flipped. So that's how this thing works. If you don't discover something horizontally, you discover it vertically, and if you discover it both horizontally and vertically, it will pinpoint that bit. So in this case, we know this 0 had flipped. And this is how the block parity system works. It works at not much greater cost. How much? How do we check? How do we evaluate it? Redundancy. How much redundant data? We still have to send 1 bit with every byte. That means every 7 bits, we'll have to add one bit. Every 7 million, we'll have to add 1 million. So it's still heavy. Plus 1 extra byte at the end of the frame. That's not a lot. That's not a lot more than the last one. It's a lot, but not a lot more. So they're both bad. Parity system is bad with redundancy, and also parity block is also bad. But if this makes a lot of improvement without much extra cost, it's good. So there's not much extra cost as far as the redundancy is concerned. Speed as well, they both are great because they only use logical functions. They don't actually count, they just XOR and it works. And then the last one, it does not discover many errors. It cannot discover, yeah?
So what if multiple bits?
Yeah, okay, let's have an example of multiple bits. Okay, so here's the bits that change. Let's change another bit. For example, let's change. So now we know this bit has an error, but let's pretend we don't know. And also this bit changed. So now we have 2 bits change. So now, when the receiver receives this and counts 1, 2, 3, you find 3. You say, whoa, there's no error. That's odd, even though we have 2 bits change. But let's count them vertically. So now vertically, the first column has 3, but the second column has 2. And now we say, hold on, there's something wrong here. And also column number 4 has 2. So even if we don't discover horizontally, we will discover them vertically. So this one covers us. So all the errors that cannot be discovered, if we get 2 errors in 1 byte, or 4 or 6, and we cannot count them, still difficult to discover, but we will discover them vertically. And the same, if we get in a vertical line 2 errors or 4, and we don't discover them, we will discover them horizontally. So it's a lot better than the previous system. All right? But there is one situation. There's one situation in this system where we can get more errors and we cannot discover them. We get actually 4 errors and they cannot be discovered. And that situation is, guys at the back, well, near the back there, 2 of you, if you don't stop talking, I'll ask you to leave. Please, cut down on the talking. Right, so see, these 2 bits have errors, but we are able to discover them. Imagine if these 2 bits also flipped. Any kind of corners of a box in this matrix. So these 2 bits as well, let's say they changed to zeros. Or if they were 0, we change to 1, or whatever value, we just flip them. Now we have 4 errors. And as you can see here, if you count them, if you count this horizontally, 1, 2, 3, 4, 5, we did not discover the error. And also here, we did not discover the error, 1, 2, 3. So maybe we hope we discover them vertically, but now if we count vertically the second column, it says 1. It's a number. And if you count this, also 1, and that's an odd number, and that's the only error that cannot be discovered. If we get 4 bits that make up the corners of any box in this matrix. For example, if you take this bit, and that bit, and that bit, and that bit, here's a rectangle. Those 4 bits, if they are gone, they would not be discovered. Any box or square or rectangle you can fit into that matrix, the corner bits in that box, if they all, those 4 flip, they will not be discovered. Okay, so it's a lot better than the previous system, and this is a known thing. It doesn't easily happen that you only get those 4 bits. Normally, if you get some noise, you get a few bits together in the same byte, or maybe the next, those 2 bytes. It's very unusual that you get those exact 4 bits. So it performs much better from an error discovering capabilities. It discovers a lot more errors, and it's the same speed and almost the same redundant data. So this is a big improvement to the parity error detection system. But it's still major disadvantage. So it's fast, it discovers a lot of errors, but still has a lot of weight, extra weight it carries, a lot of redundant data. 1 million, if you're sending 7 million bytes, you have to send 1 million bytes of redundant data. 1 in 8 is very ratio of 1 to 7. So if you are asked how much redundant data does the parity system have, you need to say 1 in 8 is redundant, or 1 to 7, like the 2 dots. 1 to 7 is a ratio. 7 is data. You have to send 1 extra data of redundancy. Okay. So which one is better, the parity system, the parity bit, or the parity block error detection system? The parity block. How, is it faster? Is it better because it's faster? No. Or is it better because it has less redundant data? No, but because it has more errors. So, but this is not really very common. It was used, but not very common in networks.